Lesson 18 demo. Today we reviewed trigonometric functions so that we can find and use derivative formulas for them next class. Remember, the way to convert between degrees and radians is to use the identity 180 degrees is equal to pi radians. In calculus, we assume radian mode unless noted otherwise. There's a very good reason for doing this, which will become clear when we get to derivatives of the trig functions. That should be next class. One important key to success with trigonometry is familiarity with the unit circle. Let's fill in a few of the blanks in the diagram below. You can fill in the rest later if you wish. So here we go. So first, let's start by filling in some angles in this unit circle. So 0 degrees is this first angle and 0 radians. And then you can see I've already filled in the next one here, 30 degrees and pi over 6. Let's fill in the next couple here in this first quadrant. So 45 degrees is the same as pi over 4. 60 degrees is the same as pi over 3. And up here at the top, we've got 90 degrees, which is pi over 2. Now, I've got those ones memorized, but I struggle when I get to the other quadrants. I mean, I guess I know the, I know the degree versions. I know that's 120 and 135 and 150, but I struggle to remember the fractions for the pi's, the radian versions of these angles. They just didn't make any sense to me until one of my former colleagues, Niels, showed me the following trick. He said, consider pi over 12, which is an angle that is right about here. So this angle, pi over 12. Now typically we don't care about pi over 12, but if we do another pi over 12, that would put us right here. Let's do a different color. So this angle is 2 pi over 12, which of course reduces to the pi over 6 that we've got written down there. But the fact is, if we just keep doing multiples of pi over 12, then we should be able to reduce and figure out the these pi fractions. So I don't want to clutter up my diagram anymore. So I'm just going to put these out on the outside. So pi over 12 is the one that we don't really care about. This is 2 pi over 12. This next one is 3 pi over 12. 4 pi over 12. 5 pi over 12 we don't care about, but I'll label it. And then 6 pi over 12 at the top. We'll do 2 more. 7 pi over 12 we don't care about. And then 8 pi over 12. And so how is this useful? Well, if you take, I mean, it's easy to just write those down, right? That's a straightforward pattern. And if you reduce 2 pi over 12, sure, you get pi over 6. And if you reduce 3 pi over 12, you get pi over 4. And if you reduce 4 pi over 12, you get pi over 3. And if you reduce 6 pi over 12, you get pi over 2. And so this crazy pattern, pi over 6, pi over 4, pi over 3, pi over 2, which didn't make any sense to me, actually makes a lot of sense to me now that I understand that underneath all of this, it's just reduced multiples of pi over 12. And so skipping 7 pi over 12, but getting to this next one, which I don't really have memorized, now I see I'm just supposed to reduce 8 pi over 12. Oh, easy, that's just 2 pi over 3. And so if this is helpful to you, you can use it. You can fill in every single radian angle around this circle. Just make sure you skip the one right before and the one right after each of the axes, x-axis and y-axis. Okay, next up is filling in the coordinates of the points on our unit circle. Unit means that the radius is 1. And so if I'm coming over here and I want the coordinates of this point right here, well, that is x is 1 and y is 0. So we'll fill that in red. Yeah, let's do that in red. So 1 there, 0 there. And it turns out that the coordinates of this next point here are x is radical 3 and x is radical 3 over 2 and y is a half. And the next one, these ones are just memorized. There are patterns here. I'm not going to go into them in this video, but I'll just say that the next one is root 2 over 2 for both coordinates. And then the last one in this quadrant here is the same as the 30 degree one, but the x and y are reversed. So it's 1/2 and root 3 over 2. And this point up here at the top is, of course, a 0, 1, which I'll point out is, again, the same as like this corresponding one over here, just reversed. Right? And so to fill in the rest of them, I'll just do one more, but to fill in the rest, it's exactly the same numbers as we've got over here. You've got a collection of numbers here, x's and y coordinates. That collection of numbers simply repeats all the way around into each of the four quadrants. The only change is that some of the signs become negative. Right, everything's positive in the first quadrant, but in the other quadrants, that's not true. So for example, if I want to focus my attention here, I will make use of the fact that this is the symmetric point to this one, right? Straight across the y-axis, which means that the y-coordinate is exactly the same. So it's still a √3/2 up there. But clearly the x-coordinate is negative now. It's not positive a half, it is negative 1/2. And so I think it's good practice to fill in the rest of these things. Maybe pause the video here if you haven't filled these in already, and go ahead and fill all of them in. The other thing that I'll say is that certain trig functions are positive in some quadrants and negative in others. And so you can see I've kind of written over it, but you can see the words positive and negative right there. So in the first quadrant, all of the trig functions are positive. None of them are negative. So cosine of every first quadrant angle is a positive number. Tangent of every first quadrant angle is positive. Sine of every first quadrant angle is positive. In the second quadrant, sine is positive, and cosine and tangent are negative. In the third quadrant, tangent is positive, sine and cosine are negative, and in the fourth quadrant, cosine is positive, sine and tan are negative. And the way that I remember that is a simple mnemonic here, ASTC. All students take calculus. Sadly not true, but this tells me that all the trig functions are positive in the first quadrant. Only sine is positive and the others are negative. Only tangent is positive and the others are negative. Only cosine is positive and the others are negative. And when I say the others, I'm really only talking about the three like main ones, sine, cosine, tangent. I have been blissfully ignoring these guys, but should be easy enough to figure out because we know that cosecant is the reciprocal of sine. And so if the sine of t is a negative number, then so is the cosecant of that same t. Okay, so on the unit circle, let's fill in, we've got x's and y's we got to fill in here. So we know that sine is the y coordinate, cosine is the x coordinate, and tangent is the y divided by the x. So for example, if I asked you for the sine of 30 degrees, sine of 30 degrees, so here's the 30-degree angle, you got your x and you got your y, and I said find the sine of 30, and we know sine is always the y coordinate on the unit circle. So sine of 30 degrees equals 1/2. Okay, and then if you write the other three trig functions in the right spots, then they are just the reciprocals. Cosecant is the reciprocal of sine, that makes it 1/y. Secant is the reciprocal of cosine, so therefore 1/x. And cotan is the reciprocal of tan, x/y. Okay, number 4, let's recall some facts about functions of the form f of x equals a sine b parentheses x plus c plus d, and then the same thing with cosine. So the amplitude tells you how far you shift, how far you are stretched from the middle of your sine or cosine graph. How far is it to get to the top of the graph from the middle? And it turns out that's always the absolute value of whatever the number a is. The horizontal shift turns out is either it's c, so in this form, whatever the number c is, that's your horizontal shift, and it's either left or right, depending on whether c is positive or negative. We'll talk about that. The period is 2 pi divided by b. Remember, period is how long it takes to get one complete cycle horizontally. And then the midline is just the y coordinate of the middle of your sine or cosine graph. Okay, so let's see if we can use one of those formulas to answer 5. It says rabbit population varies sinusoidally, or cosinusoidally if you prefer, between 3,000 and 5,000 rabbits. The last 2 times the population reached 5,000 were in 2001 and 2011. Model the population of rabbits as a function of t, the number of years since 2000. Okay, so for me, I got to have a good picture before I do anything. So it says here that the t is the number of years since 2000. So 0 right here represents 2000. And it says that the rabbit population reached 5,000 in 2001 and 2011. So that means that at 1 and at 11, we were up there at 5,000. Remember, years since 2000, so that's why 2001 becomes just t equals 1. And it says the population ranged between 5,000 and 3,000. So not to scale, but I'll just put a 3,000 down here to give myself a little bit of space for my graph. And then, so I guess that means that the middle must have happened halfway between 1 and 11. So I think that's probably important for us to calculate. So halfway between 1 and 11 is 6. And at the middle, it must have been down there at 6. And so then we will draw our curve, or at least one cycle, one period of our curve. And then it continues on this way, and it continues on this way. Okay, so our goal is to find an equation for that red curve. We're either going to use sine or cosine. It doesn't matter. There's right answers for both sine and cosine. Okay, so let's see if we can figure out first the midline. So the midline is the value of d. What is the perfect horizontal middle of this thing? Well, clearly it's halfway between 3,000 and 5,000, so that's easy. That's 4,000. You could also think of that d as being the vertical shift, right? Like the quote-unquote normal sine or cosine would be centered perfectly on the x-axis or the t-axis. And so if you wanted to move that center, this center right here, up to 4,000, you'd have to just add 4,000 to the entire function. Okay, next thing to calculate. How about we do the amplitude right now? So the amplitude is the absolute value of A, and looking at our pictures, we know amplitude is how far it is from the middle to the top. So for example, from 4,000 up to 5,000, or equivalently, from the middle to the bottom, 4,000 to 3,000. Either way, it is 1,000. So the amplitude is 1,000. Now, what are we supposed to do with that absolute value? Well, nothing at the moment. It means that A is either positive 1,000 or negative 1,000. We're going to pick appropriately a little bit later on in this problem. Okay, next up, let's go ahead and do the period. So the period, we're supposed to be able to read from the picture. How long does it take to do one complete horizontal cycle, one period? One complete cycle takes up from 1 to 11, right? Because that's the high point to the next corresponding high point. And so 1 to 11 is a difference of 10. And so 10 is the period. Now the period is actually not the value of A, B, C, or D. We have to use the period to calculate the value of B. So we know that the period is supposed to equal 2 pi over B from our formula up above. So multiply both sides by B and divide both sides by 10. 2 steps in one here. So you get that B is 2 pi over 10, which will reduce to pi over 5. Great, that's not the period, that's B. That has to do with the horizontal compression or stretch of this sine function. Okay, and then finally the horizontal shift. So let's think about this. We can either think of this thing as being a sine or a cosine curve, totally up to us. What I like to do is find like a grounded point. So I'm going to draw up here like unaffected sine and unaffected cosine. So sine, we know normally would start at the origin and it's on its way up. So this is y equals sine t. And then cosine would normally start up here at 1 and of course headed down. So my normal starting points are either in the middle of the curve and heading up or at the top of the curve and heading down. And so if, for example, I wanted to focus on this kind of point, find me a point on this red curve where it's in the middle and it's on its way up. So it's going to be in the middle someplace over here, but I don't actually have an easy way to know what that number is yet, so I'm not going to pick that point. I haven't drawn anything out there. So it's in the middle right here, but it's on the way down. So that's not normal sine t. You could actually use this point and call it negative sine t if you wish. But there is a point which is in the middle on its way back up. And so if I focus on that point, let's put that one here in green, this one right here. So my sketch is off a little bit, but hopefully you believe that that point is exactly halfway between 6 and 11. And so that number right there, I'll put it again in green, what is halfway between 6 and 11? 8.5. Okay, and so if I wanted to treat this thing like a sine function, then that 8.5 would be my horizontal shift. I could think of this curve as starting here, and now it looks like an unaffected sine graph. There's one period, and you notice that it started in the middle on its way up. And so I could think of shifting my sine graph. Normally it would want to live here, but I need to shift it from its normal position 8.5 units to the right. And so when I want to shift to the right, I need that 8.5 to be negative. So one possible version of my function involves using a sine graph, in which case we're letting c equal negative 8.5, which corresponds to 8.5 to the right. And so let's just write our equation here using all the values a, b, c, d that we just figured out. The formula is up at the top there, but I don't have room for it. So you've got it on your page, but it was y equals f of x equals, but let's call it f of t in this case. Okay, f of t equals. All right, so the first thing is the a. Its absolute value is 1,000. And the only choices are 1,000 or negative 1,000. But remember, we said we were picking this point, which means it looks like a normal sine curve. It's not an upside down sine curve. It's a normal sine curve, which means we just pick a positive 1,000. But if instead we wanted to pick this point in the middle, and we could call it a negative 1,000, a negative sine curve. Either way is fine. Okay, 1,000, sine of, okay, the b comes out in the front. That's a pi over 5. Really important that you remember to put parentheses right here. T there, and then it's supposed to be a plus the c, but we said c was negative, so it's really minus 8.5. That takes care of shifting the normal sine curve 8.5 units to the right to make it quote unquote start here. And then plus the d value, which is 4,000. So I think that right there is a perfectly good formula for the red curve graphed above. But if instead of forcing this to be a sine function, you wanted to force it to be a cosine function, let's come back up here to our orange graph. We know cosine normally starts right here at the top on its way down. So looking in our one period of this cosine graph, find me the one point which is at the top and on its way down. So that's the starting point. I guess you could also call it the ending point, but we're going to call it the starting point right here. And so in this case, the value of c is just 1. And so our normal cosine curve would start at the top and go down. And we're trying to take that normal unaffected cosine curve and shift it 1 unit to the right. And so again, we need that to be a negative 1 for c in order to shift to the right. So I'll say or f of t equals 1,000. Now we're saying cosine pi over 5 t, and then we said minus 1, shift it 1 unit to the right, plus 4,000. Okay, so one thing I really like to do after I've tried these, if I have a graphing calculator handy, is actually graph to check my work. So here we go. Y equals, I'm going to type in the sine graph first, 1,000 sine. As soon as I hit that sine button, a little bell goes off in my head that says check the mode, make sure we're in radians. The one spot in this problem where we chose radians was right here, 2 pi over b. That was the radian version of the period formula. Okay, so we got 1,000 sine pi over 5 parentheses x minus 8.5 close parentheses plus 4,000. Okay, I'm going to start there, and I'm going to go to my window here. Now, this window is no good. It's not going to show us anything because this graph lives up here between 3,000 and 5,000. So I like to be like really neurotic about these sine functions and cosine functions. I'm going to type in specifically one period. 1 to 11 was our period. And then I'm going to be really tight with my window, 3,000 to 5,000. I don't know, maybe we can go by 500. And if this worked, then we should see exactly one cycle, starting in the top left corner, in this case hitting the very bottom at the middle, and ending at the top right corner. That is just a thing of beauty that convinces me that I have done this equation hunting correctly, right? It's perfect, it's tight, everything worked out. Okay, but we also came up with a cosine formula, so let's try that one too. 1,000 cosine of same pi over 5, parentheses x, but this time was a -1 for the cosine, close, close, plus 4,000. Now, if I did this correctly, I'm not going to see anything when I hit the graph button. So what we're going to do instead is we're going to come over here all the way to the left, and we're going to highlight this thing, and we're going to hit enter, and it makes it thick. And so it's going to graph a thick version of this thing. So it should graph right on top, perfectly on top of the sine function, which we already graphed. Oh, so wonderful. All right, so I'm feeling good about both of those. There are, of course, many other answers. You might get some practice by trying to force this to be not sine, but negative sine. Trying to force this to be negative cosine. If you could do that, if you could write 4 different versions of this graph, write 4 different versions of the equation, 1 sine, 1 cosine, 1 negative sine, 1 negative cosine, then you surely know what you're doing. Okay, part B says between 2040 and 2057, when will the rabbit population be 4,500? We're going to do this one algebraically. Okay, so it doesn't matter which one we pick. I don't know, this one has a 1 instead of a decimal number, so I'm going to pick the bottom one. So that'll be the equation that we focus on here. And we're looking to figure out when the population will be 4,500. So that 4,500 is clearly the value of f of t. So we're going to put 4,500 right here and copy the entire equation. Okay, and we're going to solve this equation using trigonometry. No calculus here. There's no calculus today at all, actually. So let's go ahead and solve this thing using trig. So first step is to isolate the cosine part. So I'm going to highlight this thing. This is what I want to get by itself, and then we'll have to do some analysis at that point. But that means that the first priority is to move the 1,000 and the 4,000, but of course you have to do it in the right order. You got to move the 4,000 first. So we subtract 4,000 from both sides. And then we'll divide both sides by 1,000, and that makes just a half on this side. That's nice. Okay, and so now we've done task 1, which was to get the trig function by itself. That cosine is now by itself. So cosine of some angle, it's a complicated angle in here, but I'm just thinking of this as cosine of theta, if you like. And so I'm just looking for places where cosine of theta is equal to 1/2. Okay, let's use the unit circle. We know that cosine is the x-coordinate. And so we were looking for places where the x-coordinate is a half. X-coordinate is a half. Okay, I've got one of them here. It's not this one, that's a y-coordinate of a half. It's this one right here, right? So one of our angles is pi over 3. Remember, radian only. We're not choosing the 60-degree version of this angle. We have to choose pi over 3. So for sure, 1/2 is the x-coordinate there. But there is one other point where 1/2 is the x-coordinate. It's not labeled at the moment because I didn't fill in the entire unit circle. But the other spot where the x-coordinate is a half is the same point, but the symmetrically, oh, that's not quite straight, the symmetrically opposite point right on the other side of the x-axis. So this point right down here, let's fill in the coordinates of that one. That is a half. And then instead of √3/2, it's actually negative √3/2. And this angle, this one right here, so if we had figured out what that one was, let's see if we can do this real quick. I'm going to count backwards with my pi over 12s. So normally 2 pi would be 24 pi over 12, 23 pi over 12, 22 pi over 12, 21 pi over 12, 20 pi over 12. 20 pi over 12, reduce both by 4, 5 pi over 3. How about that? Okay, so this angle right here is 5 pi over 3. Okay, so therefore our two angles, remember we were solving something like cosine of theta. It wasn't theta, it was more complicated, but this is the form of our equation. Cosine of some angle equals a half, and we just discovered that there are two answers to that one. Theta is equal to, so the angle at the top that we found was pi over 3. Was this one right here where we had a half was pi over 3, and at the bottom where we also had a half for the x-coordinate was 5 pi over 3. So theta equals either pi over 3 or 5 pi over 3. So those are the things that we're going to grab and write on the next page, and that's how we use the unit circle when we have nice angles like this. That 1/2 was a nice thing. You might think that somebody chose that on purpose. Okay, so we said that theta, I'm going to, don't copy that theta, I'm going to change that in a second. Theta is equal to, we said pi over 3, or we said theta is 5 pi over 3. Move this, don't quite have space here. Pi over 3, or theta is 5 pi over 3. But theta was just a simplified version of what we really had. What we really had wasn't theta, it was all this. And so I'm just going to erase those thetas and put pi over 5 times t minus 1. So do copy it now. So these should both have been pi over 5 times t minus 1. Okay, but I make it seem like there were only 2 solutions to our equation. Remember, the equation that we're kind of solving is cosine of theta equals 1/2. But there's more than 2 solutions, right? Like we said, pi over 3 was one angle that works. But couldn't I have wrapped all the way around the circle once and then stopped at pi over 3? So 2 pi plus pi over 3, whatever that is. Or couldn't I have wrapped around the unit circle twice and landed at pi over 3? So that would be pi over 3 plus 2 times 2 pi. Or couldn't I have wrapped around the unit circle 1, 2, 3 complete times and then landed back over here at 5 pi over 3? So that would be 5 pi over 3 plus 3 times 2 pi. And so in general, there's infinitely many solutions to that cosine equation, and we need to capture all of them right here, because I don't know which ones we want. We're looking for something between 2040 and 2057. So the idea here is to add 2 pi n at this moment right now. So we found our 2 fundamental answers, pi over 3 and 5 pi over 3. And for almost every single sine or cosine equation, you're going to get 2 fundamental answers. But then you add the 2 pi n to both of them at that moment right there. And now we've got equations that don't have any trig in them anymore. We're just going to solve these standard looking equations for t. So I'm going to move this one down a little bit. Okay, so to solve the first equation for t, first we're going to multiply both sides by 5 over pi. So 5 over pi here, and 5 over pi here. That's going to get rid of the pi over 5. So that's going to leave me with a t minus 1 equals. Okay, so we're going to now distribute this 5 over pi here and here. So when I distribute it to the first term, the pi's cancel and I get 5/3 plus, and when I distribute to the second term, the pi's also cancel. The 2 times the n times the 5 is really just 10n. And then the last step to solve for t is to add 1 to both sides. So I'll say t is equal to 1 plus 5/3, but that's really just 8/3 plus the 10n. So I just combine fractions there. Add 1 to both sides. 5/3 plus 1 is 8/3. Okay, same deal for the second equation. Multiply both sides by 5 over pi. And then the things cancel on the left, so we just get t minus 1 on the left. And on the right-hand side, lots of stuff cancels when I distribute. So the 5 times the 5 over pi times 5 pi over 3, the pi's cancel, and I get 25 over 3. Plus, and then the 2's cancel again here, so we get the same 10n. Sorry, the pi's cancel again, and we get the same 10n. And then lastly, we'll add 1 to both sides. The 1 plus the 25/3 gives me 28/3 pi. Nope, 28/3 plus 10n. So those 2 things, we'll circle them in purple, represent every single solution to this equation right here. we plug in any value of t that has one of these forms, 8/3 plus 10 times an integer or 28/3 plus 10 times an integer, plug in any of those kinds of t's in here and you will crunch the right-hand side and you will get exactly 4,500. You will find the infinitely many times where this population is exactly equal to 4,500. So all we need to do is find the appropriate integers for n that land us in the right range, which is between 2040 and 2057. So that's it. We just need to mess around and get numbers that are between 2040 and 2057. So there's a couple of ways to do this. We'll use technology to help us here. What do I want to do? I could do, let's start with the 8/3 one. So if I did 8/3 plus 10 times 2, I'm just making up the number 2 for n, then we get 22 and change. That would be 2022 is the year, and that is not between 2040 and 2057. So how about we try 8/3 and we divide that by, 8/3, and then we add 10 times, and now n equals 2 was too small. How about n equals 3? Okay, 32. All right, now I see what's happening here. So really, I think we should just do n equals 4. And that lands us at 2042, 2042 and change, and that is one answer right there. So t equals this thing is one of our answers. And then finally, and then if we try to go again, like if we try plugging in 5, oh, that one works too. We get to go all the way up to 2057. So we've got two answers right here. But if we try to do 6, then I think that's going to land us in the 2060s, which is no good. So we've got two answers. I'm just going to record a little bit of what we've just written there. So we let n equal 4 and 5 to get 2042 and 2/3 and 2052 and 2/3. Okay, so that's all the answers for the first circled purple thing. And then the same deal for the second one. Might be the same ends that work, might be different ends that work. We just have to play. So we get 28 divided by 3 plus, so we did 10 times n. So let's see if we can do 10 times 4. Let's see if that works, because 4 worked before. Oh, great. This gives us 2049. Great. If we try to do one less, that would land us at 2039, just short of the time that we're allowed to start this experiment. And if we did one more, we get 2059, which is actually already outside of our interval. So we only get one solution from this piece of the puzzle. So 49.3 repeating when n is 4. So I think that's it. I think those are all the times between 2040 and 2057 when when the population was exactly 4,500. And I know this video is long and we've still got a little bit left to do, but I'm going to go ahead and keep pushing here and say that we can confirm our answers here. We've got our two functions. I'm actually going to clear out this first one. We didn't end up using it. So just this one function. But what I'm also going to graph is y equals 4,500, which will be a horizontal line going through the curve. But I'm not going to look between year 2001 and 2011. I'm going to look between these years right here. So that's t equals 40 and t equals 57. And let's just see what happens. So there's our very thick cosine curve. And we do have more than one period, but less than 2 periods here. And how many solutions do we see where the population exactly hits 4,500? There's one there. I think that that is 2042 and 2/3. Second one right here, I think that is 2049 and 1/3. And then the third one right here, 2052 and 2/3. And we will get the calculator to give us we'll just do one of these answers. If we do second calc and then intersect number 5, it says first curve. Currently my cursor is here. That's one of my two curves. Second curve, it automatically moves it to the other curve. And then the guess. So I wanted this point right here. So I'm just going to, it's already going to find it because it's pretty close to that point, but I'll move the cursor to roughly that point, and hopefully it tells us this middle year right here, 2049 and 1/3. Excellent. Okay, so I'm feeling good about that. And let's do part C now. Okay, so part C is the same question, but now looking for the population to be 3,700. We're going to do this algebraically, although we will need to use the calculator to help us out. I'm going to just skip to, well, so the solution technique will be nearly identical. So it's just going to be a 3,700 here. Actually, I guess there isn't really much we can skip. Okay, so we'll copy our equation. 3,700 equals 1,000 cosine pi over 5 t minus 1 in parentheses plus 4,000. Let's make sure we've got that right. That looks good. Okay, so again, isolate the cosine piece. So this is the part that I need to get by itself. So we're going to subtract the 4,000 and then divide by the 1,000. I'll do 2 steps in one there. So when we subtract 4,000, we get negative 300 divided by 1,000 is negative 0.3 equals the cosine piece. Okay, and now at this point in the problem on the one up above, we had cosine equal to 1/2, and we just went to our unit circle and we found a spot where magically cosine was exactly equal to 1/2. So where is cosine exactly equal to negative 0.3? Well, we know cosine again is the x-coordinate, and so we're looking for places on this graph where the x-coordinate is negative 0.3. And so, sure, there are 2 spots where the x-coordinate is negative 0.3. So I know that this is negative 1 here, so negative 0.3 is roughly there. And so there's a spot maybe up here-ish, and then another one down here-ish. But those spots are not any of the nice angles that we've labeled here, right? Like negative 0.3 is not the x-coordinate. That's negative 1/2, and this is negative root 2 over 2, which is about negative 0.7, and this is negative root 3 over 2. None of them is exactly negative 0.3. So we can't use the nicely marked angles here. In fact, the angles that we're going to come up with here are not particularly nice, which is why we didn't bother labeling them on this picture. But we do have the calculator. So we're going to use the calculator at this moment. So what we are going to do is take the inverse cosine. I'm going to copy this again. A little bit of space. So the way to undo cosine is to take the inverse cosine of both sides. So that's what we're going to do. Inverse cosine always goes in the front. And it's not multiplication, it's inverse cosine of both sides. So the left-hand side is just a number. We're going to get that on the calculator. The right-hand side, cosine and inverse cosine cancel. That's why we put it there. And so the right-hand side is just pi over 5 times t minus 1. So all that we have to do now is use the calculator to give us an estimate for the left-hand side. Inverse cosine of negative 0.3. Okay, here we go. Second quit. Inverse cosine. Again, anytime you hit any of these 3 buttons right here, you make sure you're in the right mode. Of course, we haven't changed, but at the start of any of these kinds of problems, go to radian mode, negative 0.3. Okay, so we're going to call this 1.875. Does that sound okay? I'm actually going to round it. Yeah, that's fine. 1.875. Okay, so this is now an approximately 1.875. That's how many radians it is. And let's go back to our previous page here. So I had said that negative 0.3 was roughly here. And what we just found is this angle was 1.875 radians. Great, that seems reasonable. I know that, that this angle over here, the half of a revolution is pi radians, which is about 3.14, so I buy 1.875 there. But we got to use symmetry of the unit circle to find the other point. So I had said that there was another point just like that one right across the x-axis. It still has the same x-coordinate, which is supposed to be negative 0.3. I was actually supposed to hit that negative 0.3 line, so let's make sure we hit it. So we hit the negative 0.3, we go to, that's close enough, right? We go to this corresponding point down here at the bottom, and the calculator is not going to tell us that answer. When we do inverse cosine in the calculator, it's only going to give us an answer between 0 and pi. It's just part of the definition to make inverse cosine a function. And so we just need to use, we need to analyze the unit circle to find the other angle. So I will label this other angle in green here. And so the other angle is going to go here all the way around to the green. That's the angle that I want. So how are we going to find that angle? Well, we got two choices. I would say probably the easiest thing, but it isn't what I'm going to do, is to say that that angle is simply negative 1.875. Right? It's just the same thing, but going clockwise, so therefore a negative angle. That's the easiest thing, but you can't always do that easy thing, so I'm going to give you a different way, which will remind us about this thing called the reference angle. So the reference angle for the red marked 1.875 angle is this thing in blue, and so the reference angle is just the shortest angle between the terminal ray of your angle and the x-axis. I know I'm saying a mouthful here, but this is supposed to be a review, so hopefully those words make sense. And I know to calculate this particular reference angle, I need to do pi minus the 1.875. Pi minus 1.875. And so that's my reference angle. We're going to do that on the calculator, but I'm not going to retype 1.875. I'm going to leave it there. In fact, I'm going to store this thing as A. I might need it again. So that's my A, and I'm going to do pi minus that A. Okay, and so 1.266 is the reference angle. 1.266. And then thinking about symmetry on the circle, we know that this angle here, from there to there, is exactly the same as the 1.266. 1.266. And therefore, if I wanted to know what the green angle is, I'll try to draw it again in green. So this green angle, all the way around to there, is from here to here, stopping that spot is pi, and then plus the orange reference angle that we just looked at, which was the 1.266. So pi plus 1.266 is what we're supposed to take away from this. Pi plus 1.266. Okay, so I'm going to undo all of this stuff because this picture is just way too cluttered. So pi plus 1.266 is what we're after on the next page. Okay, good. Pi plus 1.266. So we're going to do that on the calculator here. So we're just going to add pi to this number. Okay, 4.408 we'll say. Or pi plus 1.266. A lot of work went into that, but there's no record of it on the previous page anymore. And that turns out to be roughly 4.408. That is supposed to equal pi over 5 times t minus 1, same thing it equaled before. Okay, and if that wasn't complicated enough, remember the two angles that we just found on the unit circle, the 1.875 and the 4.408, are representative of an infinite family, two infinite families of angles that land on exactly those same angles, but just wrap around the unit circle some integer number of times first. And so this is the moment where we really need to add the 2 pi n to both of these numbers. So we're going to change colors here. I'll take these two things, rewrite them up here in purple. I'm actually going to change sides of this equation. No, yeah, we'll leave it right like this. I want this to look exactly like it did up above. So which side were the t's on? T's were on the left. So I'm going to change sides for this equation. Pi over 5 times t minus 1 equals approximately 1.875. But now we have to add integer multiples of 2 pi, any integer multiple of 2 pi. And then the other equation is the same pi over 5 times t minus 1. It's approximately 4.408, but then plus any integer multiple of 2 pi. And then we are going to solve these two equations for t, and then we're in the same position we were before. So we're going to try to do this kind of quick. So the first equation, we're going to multiply both sides by pi over 5, and then we're going to add 1. And so if we, I'll do the plus 1 right now just so that I don't forget it. So multiply both sides by the pi over 5. So the pi over 5, multiply both sides by 5 over pi. And the over pi is going to cancel with this pi right here. And so we're going to get the same plus 10n that we did before, but now we need to do 5 over pi times the 1.875. And I'm actually going to store this guy now as b, so we don't have to retype it. So pi over 5 times, nope, 5 over pi times the 1.875. 5 over pi. Okay, 2.98, good enough. And then the plus 1 makes it a 3.98. Okay, same deal with this one. T is approximately equal to, so I know for sure it's going to be a plus 10n there, it's going to be a plus 1 there, and then we just need to do the 4.408 times the 5 over pi. But 4.408 is what we call b times 5 over pi. 7.015 plus the 1 would make it 8.015. Okay, and now the conclusion here, this is supposed to be the easy part. We're looking for answers between 40 and 57. We got to pick the right values of n that will do it for us. Again, we'll use the calculator to help us out a little bit. Okay, so let's go right here. All right, so this one, 3.98 plus 10n. Because it's a 10, this is actually pretty darn easy without the calculator, but 3.98 plus, for example, 10 times 3 gives me 2033, almost 2034, but that's not in our window. If we pick n equals 4, that is in our window, so that's one answer for us. And then if we pick n equals 5, let's see if it's still in the window. Oh goodness, that is not in the window at all. But if we do n equals 5, 2053 is in the window, but n equals 6 would not be in the window. So here's my two answers, 2043.98 and 2053.98. Okay, and then the same deal for the other one. Let's see if we get one answer just like we did on the previous question. So this one is an 8.015 plus 10n. Again, because it's 10, it's really silly that I'm using the calculator here. So of course it's 2048.015. And if we did n equals 5, we're going to get 2058, which is just outside of our range here. So 2048.015. Okay, and so I think we are done. That is a long, long demo, but let's just go ahead and verify. It's really quick to verify. All we're doing is changing to 3700 for our horizontal line. And so I'll graph our thick cosine curve. And then the horizontal line will be a little bit lower than it was before. I'm really hoping for 3 answers. I got 3 answers, 1, 2, 3, excellent. Let's go ahead and find this first one this time. So second calc, intersect is 5. First curve, hit enter. Second curve, hit enter. If I hit enter now, it's probably going to find me this point of intersection, but I said just arbitrarily I want to first find this one. So we're hoping 2043.98, and there it is. A little bit of rounding stuff because I didn't store the right number like I did down here. Okay, so lots of review. Trig is not so easy, but hopefully this made some sense.